Hello students, let us continue with chapter number 2, topic 2.8, potential energy in an external field. In that first topic, potential energy of a single charge. Now students, first understand the figure. Here an external field is given. This field can be uniform or it can be non-uniform, no matter about the type of the electric field. Now in this electric field, if we choose any point P, then that point have its potential. Let this potential at point P is denoted by V. Now we have taken this point P in the electric field. So with respect to any reference point, here the reference point is O. So with respect to that reference point, the position of this point is given by position vector R. Now if in this potential at point P, if we put a charge Q at this point, then we know that will give us the potential energy. Now actually the process is like this, that in an electric field at any point the potential is there, and we are going to bring any charge from infinity to a given point. So actually for that process we need to do some work, and that work gets stored in the form of potential energy. So this concept we have already studied, and so finally we can say that the potential energy U in terms of V and Q is Q into V. We have also used this formula. Next topic is about the potential energy of system of two charges in an external field. Means if the two charges are kept in an external electric field, then what will be the total potential energy of this configuration? So let us see the figure once again. You can see an electric field and there are two charged particles Q1 and Q2. Now we have taken again a reference point. Charge Q1, its position is given by R1. Charge Q2, its position is given by R2. And the distance between these two charged particles is taken as R12. Now students, any point in an electric field has its potential. So even this point A has a potential. Let that potential is V1, and if this charge is present at this point, then we can say that it has a potential energy Q1 V1. This we have already studied in our earlier topic. Similarly, this point B is in an electric field and a charge Q2 is present at this point B. So a potential related to this point B is suppose V2, and a charge is present there which is Q2. So a potential energy related to it is U2. So the individual potential energies of these charges are given here, U1 and U2. Also, if we consider only two charged particles, neglecting the electric field, then if there are any two charged particles separated by some distance, then the potential energy related to it is given by U is equal to K first charge into second charge upon distance between them is R12. So here R12. Even this concept is known to us. So we got three potential energies. First, for the charge in an electric field. Second, for this charge in an electric field. And third, between the two charges. And so if we'll add these three potential energies, we get the total potential energy of this type of configuration or a system. So you can see here the mathematical steps that the work done to construct such configuration gets stored in the form of potential energy, and that potential energy is this, that is U1, this, that is U2, and this between the two charges. So I have written the same thing. So I hope you understood this topic also. Quite simple. You have to simply remember the concepts only. These topics cannot be asked as a theory, but in MCQ this can be asked. Now let us solve example number 2.5. In this example, the earlier topics which we have studied is used. Here, given that there are two charged particles Q1 and Q2, the magnitude of these charges are also given. One is 7 microcoulomb and the other is -2 microcoulomb. Positions of these charged particles are also given. One is having position -9, 0, 0 centimeter. Means here only x coordinate is there, y and z coordinates are 0. Means this point is on the x-axis. Similarly, the position of second charge particle Q2 is given by position vector R2 and it is 9, 0, 0 centimeter. Here also y and z coordinates are 0, only x coordinate is there, means even this charge is on the x-axis, and so here we have considered only the x-axis. Now this is the center of the line joining these two charges. So from this point O, this much distance will be definitely 9. From point O, the distance towards charge Q is also 9, and hence the total distance between the two charged particles will be 9 plus 9 means 18 centimeter. So I hope students you are getting this figure properly. Now we will start the questions asked in this example. Here we want to find first the potential energy of the system of the two charged particles. Whenever there are two charged particles separated by some distance, this system of two charges will have the potential energy which is given by U is equal to K Q1 Q2 upon the distance between them, that is r12 here. Now simply putting the values, value of K, value of Q1, value of Q2, and the distance between them. Now students, value of Q1 is given as 7 microcoulomb. So I have written here 7, and micro means 10 raised to minus 6. Similarly for charge Q2, the value given was minus 2 microcoulomb. So minus 2, and for micro we have written 10 raised to minus 6. While the distance R12 is 18 centimeter, and so we need to convert this centimeter to meter, and so here 10 raised to minus 2 is multiplied, so that the centimeter gets converted to meter. Now calculation part you can do yourself using calculator. Now I don't think you will have any difficulty in the calculation, and finally you will get the answer. U is equal to minus 0.7 joule. So this is about the potential energy of the system of two charged particles. Now next is work required to separate these two charged particles to infinite distance. Now we know that when the two charged particles are separated by infinite distance, then their total potential energy will become zero. At infinity, the potential energy is zero. Now here already we know that the potential energy at present is minus 0.7 joule, and now if we'll separate these two charged particles to infinity, then their potential energy will become zero. So we will consider this as the initial potential energy before separation, and afterwards, after separation, the final potential energy will become zero. And so work required to be done, W, is equal to change in the potential energy, final potential energy minus initial. So here final potential energy is zero, because the charged particles are separated to infinite distance, minus initial potential energy, which is minus 0.7. So minus into minus plus. Hence the work required to be done to separate them to infinity is 0.7 joule. You can easily remember in short that whatever the potential energy is there, its opposite will be the answer. Now next is, given that this system of charged particles is kept in an external electric field. Now here electric field is given, E is equal to A into 1 upon R square, where constant A is given as 9 into 10 raised to 5 coulomb per meter square. Now students, we know that when the two charged particles, the system of two charged particles, when it is kept in an external electric field, the potential energy of that configuration will be given by this. The total potential energy is nothing but the potential energy of first charged particle in an electric field. It is also second charged particle in an electric field, and also the two charged particles and the related potential energy. Students, theory related to this situation we have studied in topic number 2.8.2 in our today's lecture only. Let me show you that. You can see here there is a system of two charged particles separated by some distance, and this system is again kept in a electric field, and for that the potential energy is obtained. So this we have already studied. So even in this example we have to apply the same concept. So now let us start. The total potential energy in an external electric field will be given by this formula. Let me give this equation number 2. This is equation number 1. And now what is potential energy U1? It is the potential energy of this charged particle Q1 in an electric field. Now U is equal to Q into V1, that we know, but here little difference is there. What is V1 here? It is potential at that point where this charge is kept, and we know that potential V is equal to E into distance, and here the distance is R1, and electric field is E1 where the charge Q1 is kept. Here the electric field is not uniform, and that's why at different points the electric field will be different, and so the potential is also different. And so here we have used the same concept that V1 is nothing but it is E1 R1. Now next, what is electric field E? That is given. It is this A upon R square into R1. This A upon R square is from equation number 1. You can see here in equation number 1 it is given. So electric field E1 is kept here. Now R square in denominator and 1 R in numerator, so they will cancel 1 and only 1 R1 will remain. That you can understand easily. So we obtained U1. Similarly, now what will be U2? For charge Q2, directly we can write U2 is equal to Q2 A upon R2. This is as similar as this only. So now U1 is obtained, U2 is obtained, and finally left is U. What is U? It is the potential energy of two charged particles before they were kept in electric field, and that is already obtained in first part, that is A part. We obtained that answer as 0.7 joule, so we can directly keep that. So now putting all the given values, first is Q1 which is given 7 microcoulomb, so 7 into 10 raised to minus 6. Value of A is given as 9 into 10 raised to 5, and distance R1 is 9 centimeter, and so here we kept as 9 into 10 raised to minus 2, which is now converted in meter. Similarly for U2, the charge Q2 is minus 2 into 10 raised to minus 6 coulomb. value of A is as it is because it is constant, same as this, and distance R2 is again 9 centimeters. So we have converted this into meter, so there is 10 raised to minus 2. For this you have to once again see the figure. Why this distance is 9? Why this distance is 9? It is given in the figure. And value of u earlier, which is given in first part, that is A part, that is minus 0.7. Now after calculation we can get this answer. This 50 is for this two and minus 0.7 is this, and so final result, that is total potential energy of that configuration, is 49.3 joule. So this is about example number 2.5. Students, whenever you see this example, you have to sit with a paper and a pen so that you can calculate this required calculation. Now today's last theory and most IMP theory. This theory can be asked in 2 marks. Here we have to find the potential energy of a dipole in an external field. Now we know in chapter 1 we have studied about the dipole which is kept in an external uniform electric field. What happens when the dipole is kept in an external electric field? We know that torque acts on it, and we know that formula which we have obtained in chapter 4 is tau is equal to P cross E in vector form. If we remove this cross product and only write the magnitude of the torque, then it is Pe sine theta. So here we have given this equation number 1. Now let us see the figure. Here in figure you can see an electric field is given. As these electric field lines are parallel, we can say that it is a uniform electric field. This is the x-axis and the center of the dipole is on the origin of the x-axis. The charges minus q and plus q are shown here, and we know that the dipole moment of any dipole is from negative to positive, so that is also shown in the figure. Distance between the two charge of a dipole is always taken as minus 2a. So this is about the figure. Now students, if we want to rotate this dipole in an electric field, then we need to apply an external torque. Otherwise what will happen? If we'll put the dipole in an electric field, then it will rotate due to that electric force, and we can say that the torque acting is due to the electric field. But if we want to rotate opposite to that, then we need to apply an external torque. And suppose we have applied the external torque and the dipole gets rotated, and so this angle will change. So here the displacement is in terms of angular displacement, and as we have given the angular displacement, the work is done. Now let us move to the mathematical steps. Also, one thing is important, that when the dipole is kept in an external uniform electric field, the net force acting on it will be always 0, but the torque is not 0. Now, suppose when the external torque is given, the dipole rotates, and suppose the change in the angle is from theta naught to theta 1. Theta naught means it is an initial angle, and after the application of external torque, the new angle is theta 1. Now here we have to rotate this dipole in such a way that its angular acceleration is 0, and so as the acceleration is 0, its angular speed will remain constant. Now the work done by this external torque is given by dW is equal to external torque into small displacement d theta. See here, actually we are going to displace from theta naught to theta 1, but first we will consider a very small displacement, so work done for that will be also very small, denoted by dW. And then to find the entire work or the total work, we have to integrate, and the limit of integration will be theta naught to theta 1, means initial angle to final angle. So our next step is that only, that total work done is integration of dW. Now what is dW? So from this equation number 2, we'll keep this value and limits initial limit to final limit of integration. But what is torque? Torque is nothing but it is Pe sine theta from equation number 1. Now here external electric field is constant, even the dipole moment is also constant. So we know that during integration or differentiation, the constants are to be taken out. So remained is sine theta d theta. Next step, integration of sine theta is minus cos theta. We have studied about integration and differentiation also in 11th standard. So according to that rule, integration of sine theta is minus cos theta. Now after integration, we'll put the upper limit and lower limit, means upper limit minus lower limit. So first we'll put theta 1 in place of this theta, so minus theta, that is upper limit, minus lower limit. Again lower limit is theta naught, so we have kept here theta naught. Finally work done, W is equal to Pe cos theta naught. See here, this is minus into minus plus, so this positive term we are keeping first, and this term which is negative we are keeping it afterwards. Let us give this equation number 3. Now if we consider this theta naught, that is initial angle, to be pi by 2. Why we are taking this as pi by 2? Because we have to consider here that initial potential energy of the dipole is 0, and after rotation, when the angle becomes theta 1, we get the exact value of potential energy. So to keep that initial value of potential energy 0, we will take initial angle as pi by 2, and we know that cos pi by 2 will become 0. And so from this equation number 3, if we'll put initial angle pi by 2, this term becomes 0, and now only one theta is remained. So in place of theta 1, now we'll simply place angle theta. So it is here. If this is 0, then only this term is remained with this minus sign is taken out. And so potential energy U is equal to minus PE cos theta. Whenever there is a negative sign and if there is a cos theta, and if the product is of two vector quantities, then definitely it is a dot product of two vectors. Hence finally we can write in terms of the dot product of two vectors as U is equal to vector P dot vector E. So this is nothing but the potential energy of an electric dipole kept in a uniform electric field. Students, a simple mathematical step I have taken here so that you can easily understand this theory. I hope you understood the examples done today and the theories, but I will also advise you to go through the textbook. You should have a habit of reading textbook and underlining the important points.